Alright guys, welcome. Today we're going to talk about magnets and electricity. You should have a good bit of already content knowledge on this, but we'll review a good bit, and then we're going to do some really fun demos in class. Magnet is an object that produces a magnetic field, so that we'll talk a lot more about that here in a second. And we can find them naturally, or we can also make them in a lab, which gets to be a little bit interesting. So if you're going to find natural magnets, they have to be of 4 different elements here. They've got to be iron, cobalt, nickel, or gadolinium. Other than that, all of these other metals and non-metals are not naturally found to be magnetic. So other magnets that we see on this Earth, compasses, we use them all the time, and the Earth itself, actually, believe it or not, is one very large magnet. This is hence the reason we say the Earth has north and a south pole, right? So, like I was saying right there, magnets have 2 poles. They have a north and a south pole, and if you remember what we were talking about last class with electricity, we showed you a new way to draw kind of electric charges coming out, and then here we have those magnetic fields coming out with the arrows, and if I put a north end right here by another north end right here, we see that these arrows begin to repel one another. In contrast to that, if I put a north end of a magnet by a south end of the magnet, all of a sudden you see these arrows line up, and we have this nice fluid movement of what we call the magnetic field lines. Now remember, there's not actually any movement here. This is just a way for us to help recognize a very conceptual topic. Magnets are permanent or temporary, but regardless of whether they're permanent or temporary, we have atoms, or the electrons specifically, that are always going to line up. And if I take one solid magnet, cut it in half, I then all of a sudden have 2 magnets, and they have their own north and south pole, and I can do that again, and all of a sudden we have more magnets with north and south poles. So regardless of how many times you cut a magnet, the north and south poles will still appear in the new magnet. Permanent magnets they're magnetic all the time, hence the name permanent magnet. There's no real trick to that one. We can change certain objects, so let's say a nail or a paperclip like we have right here, into a magnet by simply taking this nail or paperclip and rubbing it against a magnet. And what that's going to do is it's going to align the electrons within these objects. But unfortunately, this isn't a permanent thing. It's temporary, and eventually this paperclip will lose its magnetic properties. Here we have some really good drawings and representations of magnetic field lines. We notice that the arrows are always going to come out of the north end, and they're going to come into the south end. Now, as conceptual as this may seem, a lot of times we would draw these pictures just to help us understand things better. And we'll do this in class for you tomorrow, if you took a bar magnet and you placed a sheet of paper on top of it, and then you place iron filings over the top. The iron filings form these really neat patterns just like this, and essentially what you're seeing here is exactly what this is right here. This is just the actual representation of it. The iron filings line up with these magnetic field lines that we're actually drawing here. Notice that really the accumulation on both ends of the magnet, this tells you that the magnet is really, really strong at these points. And as we move away, so maybe out in this region, the magnet has less of an attractive force out here. So the closer you are to the magnet, the more attractive it is, and the further away you are, the less attractive it is. And the way we draw this is, we draw this by putting our lines really close together. So lines that are closer together, like in these regions, the magnet is stronger compared to in these regions out here, where the magnet is slightly weaker. So we kind of see the same thing again here, iron filings lining up, and then we have the magnetic field lines of the Earth coming out of the north, going into the south. This is where things get a little tricky, and then we're actually going to have a little fun with this in class. But magnetism and electric currents can go hand in hand. In other words, electric currents produce magnetic fields. I know that's kind of weird to think, but if I have a wire and I run electricity through it, so you can see this wire right here that's just been looped, and I run electricity through it, all of a sudden this wire becomes a magnet, and magnetic fields are produced around that magnet. Here we have a kind of a demonstration. This is just blue paper, and we have our wire looped around here. You can see it looks like threaded there. And then we attach that to a battery, and the iron filings, you can see, begin to line up. And there's this magnetic field around these can be incredibly strong magnets. We usually use an iron core, and then we wrap wire around it. So we can make a really simple one, which we'll do in class. We'll take a nail, wrap a bunch of wire around it, attach a battery to it, and all of a sudden we have an electromagnet. So strength depends on a few things here. In other words, we can make these stronger, or we can make these weaker. So unlike normal permanent magnets, electromagnets can be controlled. We can make it stronger by adding thicker wire. And you should understand this because, well, it's less resistance. We can increase the number of loops. So the more loops I have here in my magnet, it means the stronger the magnet will be. We can add more current. That's really easy. We just add a bigger battery. So the more push coming from the battery, wherever it is, means more electrons are going to flow through and you have a stronger magnet. And then the size of the iron core. Let's say we increase the size of this nail, more iron, more potential to be greater magnet. So why are they useful? So really, first and foremost, they can be turned on and off, which is huge. This is really important to us. In other words, if we didn't want this to be magnetic anymore, we would just unplug the battery or open the circuit. And we can control their strength. So unlike, like I was saying, with permanent magnets, those are as strong as they are, and we really can't do too much to change them. But electromagnets, on the other hand, we can change it just like everything we talked about last slide. More current and voltage, bigger iron core, more loops, and we can create a stronger magnet. So two really big advantages there to using an electromagnet compared to a normal permanent magnet. In the same field, we begin to talk about motors. And we can use electric motors. And this is going to be really complicated, and if you don't quite understand this, don't worry about it. We'll explain it better in class when we can kind of draw out some diagrams. Electric motors change electrical energy to mechanical energy, and that makes sense if you think about our energy conversions from last unit. So of course, if it's an electric motor, it's going to run off electricity, and then let's say it causes your car to move, well then that's kinetic energy. In a more general term would be mechanical energy. So how do we do this? We run electric current through coils, and that creates this electromagnet. Well, let's see, here's our iron core, this white piece. This green represents our wire, and then we actually put this electromagnet around another larger magnet. And all of a sudden, if this electromagnet turns on, it begins to spin, okay? And this spinning, if attached to, let's say, an axle, which is this black dot right here, think axles attached to the wheels of cars. If this begins to spin, then your axle spins, and if your axle's attached to some tires, then all of a sudden your car is going to begin spinning. And we're actually going to show you that tomorrow in class. We're going to make a miniature one of these motors. So the opposite of a motor would be an electric generator. So whereas a motor takes electrical energy and converts it to mechanical, a generator is going to take mechanical energy and convert it to electrical energy. Just think about when your power goes out, let's say a hurricane, and all of a sudden we lose power. Turn one of these generators on, and it's going to begin turning the gears inside here, and then producing electrical energy so we can run our houses off. And it produces AC current, that alternating current we were discussing in a couple PowerPoints ago. In other words, the electrons within the circuit go back and forth, creating that flickering that we discussed. But generators use an electromagnet, and they use that electromagnet that spins, and that spinning is what produces this alternating current. We'll have a couple videos for this, and we'll actually show you one of these in class. So that's it for tonight, and I guess what I need to help out finishing is the extra credit. So the last part of the extra credit is a picture of a series circuit.